Hello everyone and welcome back. So what we're going to be doing today, I believe it will be Friday by now, is calculating our Ka value given a pH value of a solution. So here we have a 0.1 moles per liter solution of HClO, and this is a weak acid which has a pH of 4.23. So we are asked to calculate Ka. But why are we calculating Ka? Well, we need to determine, is the H plus ions coming from our HClO, or is this a very weak acid and our H plus ions are actually coming from the autoionization of water? So in order to do that, the very first step that we're going to have, as we have seen many times before, is just simply writing out our Ka equation. So just like anything else, if we have our reaction, all right, I'll just write it over here. So we're going to have our HClO, right, and it is going to react in equilibrium to produce H plus ions and ClO minus ions, all right. So by looking at this equation, we can tell that our Ka is going to be equal to the concentration of our H plus times the concentration of the ClO minus all over the concentration of HClO. Right? We've seen this many times before now. All right. Now, using this, we can see that for each mole of H plus that is produced, right, 1 mole of ClO minus is reduced. So therefore, at equilibrium, our concentration of H plus is going to be equal to our concentration of ClO minus. All right. So we need to see at equilibrium that our HClO, just because this is such a weak acid, right, our HClO we're going to see is approximately equal to, right, we're making this assumption right off the bat, right, was approximately going to be equal to 0.1 moles per liter, because this is such a weak acid. Right? So what we're going to do is we need to determine the H plus. So we need to figure out, well, what is our concentration of H plus ions in solution at equilibrium? And as we know, we've already used this equation before. Our pH is equal to 4.23. And we can determine then that our concentration of H plus ions is going to be equal to 10 to the negative pH, or concentration of H plus equals 10 to the negative power of 4.23, which we just pulled from here into our pH value. All right. So what we're going to do with that is we're just going to quickly solve this. So just with your calculator, we're just going to we're going to go 10 to the power of negative 4.23, and that is going to give us 5.9 times 10 to the negative 5. So our concentration of H plus ions at equilibrium is going to be equal to 5.9 times 10 to the negative 5 moles per liter, right? And using this, as we determined earlier, right, our H plus and our ClO minus, because this is a 1:1:1 ratio, we're going to have the exact same amount of ClO minus in our equilibrium as we have our H plus, right? So using this, we can determine that we are able to now put everything into our Ka equation in order to solve for Ka. All right. So we're just going to have, again, Ka equals our concentration of H plus times the concentration of ClO minus all over concentration of HClO. All right, up here we determined that our HClO, because we're assuming that this is a very weak acid, is going to be equal to its initial concentration or approximately equal to it. But we are going to see some changes in our H plus and our ClO minus. right? So with my Ka, is going to equal my 5.9 times 10 to the negative 5 for my H plus, and as we know, our ClO minus is going to be the exact same. So that is also going to be 5.9 times 10 to the negative 5 all over our concentration of HClO, which is going to be approximately 0.1 moles per liter. And once I take all that, I'm going to punch it into my calculator. So what I'm going to do is I'm just going to take my 5.9 times 10 to the negative 5, right? And just for simplicity's sake, just because I'm multiplying them by each other, right? I'm just going to square that value just to make things a little bit easier on my calculator. Oops. And when I square it, I'm going to get 3.48 times 10 to the negative 9. And then I'm going to divide that value by my 0.1, which is on the bottom, or my denominator. And that is going to give me 3.48 times 10 to the negative 8. Right? So that is going to be my Ka value. Ten to the negative 8. Right? However, we made an assumption earlier, and we weren't quite able to have a Ka to compare to our initial concentration. So what we need to do now is we need to be able to check in order to see that the assumption that we made is a valid assumption. So we assumed that this was going to be a very weak acid, and our X value is going to be so small that we were going to basically be at 0.1 moles per liter again. So what we need to do is we need to actually make sure that that assumption is correct. Right? So we look that, if I just bring it over here, all right, our Ka value that we calculated was 3.48 times 10 to the negative 8, right? And we can now look that our Kw is 1.0 times 10 to the negative 14. So we can see that our Ka, first off, is much larger than our Kw. So we know, A, that all of our H plus ions, most likely, or most of them, came from our HClO. Right? So that's our first assumption that we were able to check. Right? Our second assumption that we need to check is the assumption that our equilibrium concentration of HClO is going to be approximately equal to 0.1 moles per liter, because we thought that this was going to be such a weak acid that we are going to see that this is going to be an assumption that we can make. So we're basically going to reverse engineer in order to solve for our rule of 100. So as we know, with our rule of 100, we take the concentration of whatever acid we have, HA, in this case it is HClO, and we're going to divide that by our Ka. So if we input our Ka that we calculated into here, as well as our initial concentration, right, we're going to see that it equals 0.1 moles per liter, all divided by 3.48 times 10 to the negative 8, which was our Ka value that we calculated earlier. And if I punch that into my calculator, I'm going to take 0.1, I'm going to divide by 3.48 times 10 to the negative 8, and this is going to give us an astronomical number, 2.87 times 10 to the 6, which is obviously much larger than 100, right? So our assumption is correct, right? And we can say that all of our work that we have done here in order to solve for our Ka was within reason, and our assumptions were correct. So now what I want you to do quite quickly is to go through your practice problems, right, on page 521, right, and it's going to be practice problems 1 and practice problem 2, right, are on the top of the page. And then what I will do is I will come back once you're finished, just click on part 5, and we will resume.